Started. Today we're going to continue the discussion of PCA. I don't know if you all have heard of KD Nuggets, but it's a blog around data science, and they listed a whole bunch of algorithms that machine learning engineers need to know, and I think hopefully we've covered the ones up to this point, and then the rest of them we're basically covering now. So PCA is what these lectures are about. SVD, I'll mention it today, and then ICA you can find in the bonus slides. So last time we talked about PCA, and there were many ways of looking at it, and I don't know if that was helpful or confusing or what, but you could look at it as in the visual way. So we're projecting the points down to some subspace that is lower dimensional, and we can't really look at it for that many dimensions, but we looked at projecting 2D down to 1, 3D down to 2, and 3D down to 1. And we played around with those notebooks, which are available to you as usual. And then we talked about it from the k-means point of view, which is like, well, this is kind of like k-means, except that it's, instead of z having to be a 1 and the rest zeros, meaning each point is approximated by a single mean, we're now allowing mixtures. And I kind of like that way of thinking about it, but kind of don't. I guess I like it because it relates to things we've already done, but I guess once you cross that bridge and fully understand PCA, I don't know how helpful it really is anymore, because we're not doing clustering. We're doing something different. Another point of view on PCA that we talked about last time was this learning a basis. So you have some space, d-dimensional space. You need d basis vectors to span that space. And we're going to restrict ourselves to k basis vectors instead of d, k less than d. So you can only span a subspace. Let's find the optimal subspace to project onto. And we're going to approximate our data only by living in that subspace. And so W contained the basis vectors, and Z contained the coefficients. And then we also talked about it as matrix factorization, yet another way of thinking about this same thing, which is we're factoring a matrix X approximately, not exactly, into a matrix Z times a matrix W. And as another visual, one way we could think about this is we're breaking things down into parts. So I didn't really go into this in the first lecture, but you can think of this is your training example, and I have a bunch of these parts. This is a picture, an image of a digit, and this is one of those, and 0 of those, and 1 of those, and 1 of those, and so on and so forth. And we are doing this, but we're not restricting ourselves to 1s and 0s. So we have a whole bunch of language that comes along with PCA. The W vectors, you could call them the basis vectors, the factors, the principal components, the parts. So there's unfortunately a bunch of words, and I may use a range of them without really thinking about it. So it's good to be able to use all those different words. We also talked about, last time we did plenty of this geometric stuff, as I mentioned. One thing that I didn't mention, well, I kind of did, but maybe not explicitly, is that you can think of projecting your points onto a subspace. In this case, you start with 2 dimensions and you project onto a line. But another way you can think about it is rotating your data. Why? Because I said last time that the z values are your position in the new coordinate system. So if k equals 1, z values are just a single number, which is where am I along that line. And so if I kind of turn things like this, then my z just kind of looks like a regular variable, because that's how we draw regular variables. We draw them horizontally, right? But I had that plane projecting from 3 down to 2 dimensions, and I rotated the thing in the notebook so that we were kind of looking straight down on the plane. And so it was exactly that. We rotated the data so that we were just looking at the 2 z coordinates instead of the 3 x coordinates. And there they were. So it's, I guess, both a strength and a weakness that there's so many different ways to think about this thing. But fundamentally, if we want to just get past all the talking and get down to business, let's look at some math, right? Then we can kind of precisely define what are we actually doing here, and then all the rest becomes very valuable ways of thinking about it. But we can start to be, today, more precise about what we're actually doing. And the thing we're doing, and this may not shock you, is that we're minimizing a squared error. Well, we've been doing plenty of that in this course. And I'm pretty sure we talked with k-means about squared error. In fact, I think in your assignment you had to implement a method that computes this squared error. And you may not have been thinking about it like this. The sum of the 2 norm of, we didn't even really have z. We didn't really talk about z when we talked about k-means. And yet, that's what we were doing. With k-means, we were computing the squared distances between points and their own cluster means. Well, what is their own cluster means? The z's are just telling you which cluster mean I'm assigned to. And when you take w times z, it just picks out the appropriate row of w, because there's a 1 and the rest zeros. And that's my approximation. That's what w times z is. And then I'm subtracting that by x and squaring it. So this thing is the same function as the one you implemented on that early assignment for k-means. It is the sum of squared distances from each point to its cluster mean. And if we think about its cluster mean as the approximation or the reconstruction of that point, that's some of the language we've been using last time, then it's the exact same thing with PCA. We're just minimizing the squared differences between the original point and the reconstruction of the point, which is my projection onto the plane like we saw it last time. The square distances between the blue points and the red points, if you remember from last time, that the blue points were the original ones and the red ones were the projections down onto the plane. So that's what we're minimizing. And you can write this in a whole bunch of different ways, and we talked about this a little bit last time. But the bottom one is maybe the cleanest. So we talked about this Frobenius norm. Maybe we have. Yeah, I kind of remember talking about it, but I don't know why. In any case, oh, maybe it was for regularization with the softmax where W is a matrix and we needed sum of squares of all the matrix elements. Anyway, the little f thing is just saying it's the sum of squares of all the elements of that matrix. And what is that matrix? It's z times w, which is my reconstruction of x. It's all very densely written in matrix multiplication language. But each row of x is our training example. And each row of that product is the row of z times all the columns of w, which is exactly our approximation of the point. It's the basis vectors times the coefficients for that training example. So actually, this, to me, is like exactly what we're doing. Now it's fully specified, and you could go code this up, and we're basically done. I mean, you have to have some way of optimizing it, and that's the main thing we're going to talk about today. But you have to pick some data set. You have some data set x. You have to pick k. And then you minimize that. That's what PCA is doing. But it's not really like, it's good to understand what that means. And that's what the whole point of the previous lecture was. Any questions or comments about this? So some things to think about here. If k was equal to d, that was sort of this uninteresting case that we talked about last time. Then the subspace is just a whole space and nothing is interesting. So then this loss is going to be 0 because I'll just set z equals x, w equals identity. The difference between that will just be 0. And as I reduce k, I can expect this thing to go up, which is pretty much what we had for k-means. The more k we use, the better our loss was going to be. And so we couldn't just use our loss to pick k. And I think we talked about the elbow method when we talked about k-means, or maybe that was on the assignment. And some of that intuition for choosing k is going to carry over. OK, yeah, we talked about that. So when we talk about PCA, we usually assume that the data set is centered, which means each column of x has a mean of 0. And I kind of brushed that aside last time. But if you look carefully at all the visualizations from last time, all those lines and planes and stuff, they were passing through the origin. And we can deal with that, but the easier thing to do is just shift the data so that it's sitting around the origin, and then we can just not deal with it and have our subspace or hyperplane or whatever pass through the origin. Oops. So in order to center data, we just compute the mean of each column, meaning each feature, and then we subtract that from all the values in that column. And then the new mean of that column is 0. So we have to be a little careful sometimes. I mean, these software packages are nice because they do so much for you, but then also you might forget what they're doing. So when you call PCA and scikit-learn, for example, it just does this because it's the normal thing to do. And then if you're going and implementing PCA yourself, you just want to keep in mind that this is the standard thing. So right, the last point is minor, but just saying that you could add more variables to deal with this, but the conventional thing to do is just center the data. Right?
Can you go over why we have to do this again?
Why do we have to do this? Yeah, so if we just say we're approximating each point with some combination of basis vectors, or if we just look at what does W look like, well, when k equals 1, W looks like a line, and when k equals 2, W looks like a plane. But it looks like a line passing through the origin, and it looks like a plane passing through the origin, because it's just basically a vector. And then you can live along that vector or those two vectors. But we haven't explicitly accounted for any kind of shifting. Connor?
Is there a reason that we shift the data instead of shifting the line?
Is there a reason that we shift the data instead of shifting the line? I've thought about this before. And I maybe talked about it a bit in the bonus lecture as well. I think sometimes they're the same and sometimes they're not the same. And if they're the same, which I think they are here, then it's just simpler to shift the data. Tom?
Do you try to move outliers before you do that? Because before, it's already centered and then there's one that's miles away.
Right, so Tom is bringing up the fact that that outliers can affect the means. So I guess, and therefore affect the whole shift. So sure, I mean, that's application dependent, but I guess PCA, all this unsupervised stuff is no different from everything else we've talked about, that you may have data cleanliness issues that you may need to take care of before you start. We will also talk about a robust PCA. We won't talk about it today, but you'll implement it on your assignment 5, which is basically changing the 2 norm from the previous slide to a 1 norm. And in that case, it won't be to remove outliers. It'll be to actually find the outliers, and you'll see that on the assignment. OK. So PCA is a parametric model. we can debate whether or not let's just say the Z matrix is not parameters, okay? So let's just say, let's just call W the parameters, and then these mean vectors the parameters. And by the way, whenever you do this kind of stuff like subtracting the mean, you have to undo it at the very end. So if you're reconstructing a point with PCA, you're going to reconstruct the shifted version, and then you have to add those means back on. So that's why the means are considered parameters. They have to be stored so that when you're making predictions later, you can add them back on. And like with clustering, and we had a discussion about this on Monday, you may do this for a number of reasons, but one of the things you might want to do is learn W, and then given some new data, x tilde, you may want to get the lower dimensional representation of it. And to do that, we'll recenter them using the means of the training data. So a very common mistake is to recenter your test data using the means of your test data. But whatever you do at the training phase, you want to reproduce those steps at your prediction phase. So you need to hold on to those same training means and use those. And then we want to find Z by minimizing squared error. So I'm not going to go into this too much, the derivation of this, and we'll actually see a simpler version of this later. They'll be more useful. But the way I want you to think about it is we have some new point. We just want to project it down onto the same plane that we had before. We were just projecting all the hyperplane. We're just doing that same projection operation. Take the point, orthogonal projection onto our subspace. And there's some linear algebra that's going to do that for us. Okay. Oops. Okay, so today's lecture is supposed to be about the training, fitting, optimization, all that stuff. And one question we like to ask ourselves in this course is the thing unique? And we talked about that a lot for linear regression. What we want to know, is it convex? Is the solution unique? These kinds of things. And I'm now going to walk you through a maybe 10+ minute part of the lecture, just convincing you how incredibly not unique the solution is. So I want to walk through with you all the ways in which I can take a solution and do stuff to it and have it still be a solution. And here's where we have our geometric view and our numbers and matrices view. And the stuff we're about to do now is we're not changing the hyperplane, like the subspace that we're learning. Because for that, you can look at it and be like, oh, well, that's clearly the right one. But we're just changing W and Z around in different ways that happen to correspond to the exact same hyperplane or subspace. So we have this kind of redundancy in our representation of the subspace. So we talked a little bit last time already about the span of vectors. And I'm more or less assuming this as prerequisite knowledge. And we'll just, the definition of span is, the span of a bunch of vectors is the set of all points you can get to by adding combinations of those vectors. So the span of this vector, W1, oh, it already says it, okay. I can do all kinds of things. I can multiply it by 0.7. I can multiply it by 2.5, by negative 1.75. So by multiplying this vector by some number, I can get myself along this line. So the span of this one basis vector is a line. And that's why when k equals 1, we're learning a line, basically. And here's some data. I don't think they're that critical to the slide. But in any case, consider the span of this blue vector. Well, it's that line. And consider the span of this other blue vector. Well, it's also that line. So this is the first hint at this non-uniqueness. Here's two different W's that are actually representing the same subspace. And the Z's will have to be adjusted accordingly, but still, this is an instance of the solution being not unique. Okay, this would be a good time to pause. The point here is to be able to connect this kind of linear algebra fact that I'm showing you, which is that the span of this vector is the same as the span of some other vector. Connect that with the fact that the solution to the optimization problem that I showed you, minimize ZW minus X Frobenius norm squared, is not unique. Like, those are one and the same statement, but it's kind of a big leap to make. So are there any questions about that? Cheyenne.
Is there a way, like by assigning hyperparameters to ensure that when I run PCA on this same data set twice, I get the same?
Yeah, by the end of the next few minutes, we'll get ourselves into a situation that we can all agree how PCA is done, and when I run it and you run it, we'll get the same. So we'll first identify the ways in which the thing is not unique, and then we'll start dealing with them. Okay, so we can do the same thing with two vectors, but in fact, the problem becomes even worse in 2 dimensions. So we have these two vectors. The span is anywhere you can get by adding these two vectors. I can get here by adding them. I can get here by subtracting them, blah, blah, blah. And you can convince yourself that by taking combinations of these two vectors, I can get to anywhere in the plane. And the more reasonable, intuitive basis is the kind of orthogonal axis line basis 0, 1, and 1, 0. But as long as these two vectors aren't 0 and aren't the same or multiples of each other, we end up spanning the space. Okay. So now we have the same issue we had before. When we were just trying to span a line, we had a bunch of different vectors that span the line. Now when we want to span the plane, we have a bunch of different pairs of vectors that can do that job for us. Well, other than these two. Okay, so there's this collinearity situation that if the two vectors are multiples of each other, then they don't actually get you into a new dimension. But that aside, we can span the space. So here's the thing. In 1D, I said I wanted to go that way, and I could have a shorter vector or a longer vector, and it didn't matter. And in 2D, there's more operations I can do that change the W's but don't actually change anything. So I can still make them shorter and longer, and it makes no difference. And I can switch them. I can say this one's called W1 and this one's called W2, or vice versa. It makes no difference. So and we've used this word label switching with k-means in the same way of permuting the rows of W, which is exactly what this is, permuting the rows of W. And not only can I make them bigger or smaller, but I can also rotate them. So if I want to span the flat space in the room, I can do this, or this, or this, or this, or that. So there becomes, as you can start to see, many, many, many W's that are all saying the same thing. So that concludes kind of describing the problem, and then I'm going to talk about the solutions. But any other questions about the problem that I'm describing? And I think Cheyenne phrased it in a nice way. I mean, one way of phrasing the problem is that if I implement PCA and you implement PCA, I kind of want to get, it would be nice if we got the same results-ish. And right now, who knows? Okay, So this may not come as a huge shock to you, but the first thing we're going to do is say instead of letting the vectors be any length, let's just make them be length 1 because we can, right? We just need to pick something and stick with it, and 1 is like the most reasonable thing to pick. So we're gonna have this happen with PCA. We're gonna say the W vectors have length 1. Okay, and then we still have okay, now they're length 1, right? But we still have this problem and all that other stuff. So we're going to also ask for orthogonality, which is essentially saying that the vectors be perpendicular to each other, have 0 dot product, however you want to think about it. And for whatever space, you should be able to get an orthogonal or orthonormal or whatever basis for that space. Okay, so yeah, we still have some degrees of freedom left. So now they're both length 1, they're both orthogonal, but we still have this problem, right? The rotating them both together. So we have eliminated so far some, but not all, of this redundancy in representation. And we said that. Don't really need to say that. Said that. Okay. This is what I was looking for, sequential fitting. So the last problem we're going to solve, well, is solving, in a sense, both the rotation problem and the label switching problem, is we're going to say, I'm going to fit these things one at a time, and I'm going to pick the best one first. So I'm going to say, let's say I was just doing PCA with k equals 1. Well, what would I pick then? I would pick, I don't know, this direction. So it turns out that if I was using a higher k, I still want that direction. So I'm just going to make that be my first direction. And then I say, okay, I'm fixing that. This is my first direction. I've committed to it. But actually, just kidding, I'm doing k equals 2. What's the next best direction that I want? Again, by best, I mean to minimize that loss. And then I'll take the next one. And so on and so forth. So that's what we mean by sequential fitting. And I haven't yet said how you can do this, but that's what we're after. So it is kind of an amazing property, and I guess I haven't proved it or thought too much about if it would be easy or hard to prove, but doing this sequential fitting thing doesn't mess you up. Like if I had the best direction and then the next best one and then the next best one, that's the same as just going after k equals 3 in one shot. Okay, so if this is, if this is my data set, then it's not that interesting of an example, but okay, well if k equals 1, I'm just going to pick that line. And now we can interpret that line in a way we didn't really do last class, which is it minimizes the sum of squared distances from the points to their projections onto the line. But if I were to use k equals 2, and that's why I said this isn't that great of an example, because d is also 2. But if I were going to set k equals 2, then I would first pick this one, and then I would pick this other one. Because they're orthogonal, and they're going to be in order from most important to next most important, and so on. Okay, so this might be a little unsatisfying to you, but all I'm really going to say is you can get this thing through something called the singular value decomposition, which we don't have time to talk about. But if you want to hear more about it, you can take a course like Computer Science 302. But really, the punchline is there is some linear algebra operation that, given x, will just give you back not only a solution to that squared error loss I showed you, but the solution that satisfies all these properties. And it's unique except up to a sign. So for my first principal component, I could still pick this one or that one, and they're both length 1, and they're both in the right direction, but the sign is flipped. So other than flipping of sign, so to get back to Cheyenne's question from before, so if I implemented PCA and you did, I would now expect us to get basically the same solutions, except we might have different signs in the W's, and therefore the Z's. And you could pick some convention, like about the sign too, that'll just pin it down. Yeah. So as far as doing this in Python, here's the whole thing. I compute the means of each column. I subtract them. As you may have noticed by now, NumPy does this funny thing called broadcasting, where I'm taking x, which is an n by d matrix, subtracting mu, which is a one-dimensional thing-ish of size d, but it'll subtract that from each row of x for you. And then I can call the SVD, and I just take the last thing that comes out of it, and then it's actually giving me the full thing, like all the components, all the way up to d. So SVD is an exact matrix decomposition, where u times s times v gives you back the original matrix. It's like a true matrix factorization. Then our approximation is we're only going to take the first k basis vectors. So we're taking the first k rows of, well, we can call it W, and then we'll have our PCA. So this might seem a little wasteful to you computationally in the sense that if D is 1,000 and K is 5, why am I getting myself this 1,000 by 1,000 matrix with the whole PCA and then just taking the first 5? And there are things that will save you that, like I think scikit-learn PCA or truncated SVD or whatever. There are ways around this, but we're not too worried about it for now. So the other thing, which is why I glossed over the crazy-looking thing from before, there should be a tilde on top of that x, but we had that weird-looking thing before for getting z, but it involved W transpose, and once we have made W an orthogonal matrix, then that thing is just the identity, and so it goes away. So making W an orthogonal matrix simplifies some of the math downstream, and now to get Z, meaning the projected version, we just take x and matrix multiply it by our basis vectors, and that's the beauty of orthonormal basis vectors. Sure. Fine. Philip.
What's written in blue there is the... Oh, okay, no. You explained it right in the green, sorry.
Okay.
I was about to ask exactly what the green says.
Yeah, the green is just showing that an orthogonal matrix times its transpose is identity. Okay, so the plot thickens a little bit. As with the linear regression, we had the normal equations, which was like this nice linear algebra thing that just gave us the solution kind of in one shot. And the SVD, we can sort of feel that way about the SVD. It's just giving us PCA. I think it's kind of reasonable for you to think about it in that sort of analogy. And then with linear regression, despite having this wonderful normal equations at our disposal, we said, well, hey, maybe we want to drop this for some crazy reasons and use gradient descent or stochastic gradient or whatever many other things there are that we don't talk about in the course for a variety of reasons. One reason that we encountered being I wanted to change the loss and then I couldn't use the normal equations anymore. Another reason being maybe I had a huge data set and therefore gradient descent or SGD were going to be faster, or I didn't need that high accuracy and I'll just do a few iterations or whatever. So with PCA, it's basically the exact same story. We have this wonderful thing, but we may throw it away sometimes and just go back to good old gradient descent or SGD or whatever. But here's where the analogy breaks down. With linear regression, we still plan to get the same solution, even if we do it the hard way with an iterative optimization. Here, we lose this orthogonality, all these beautiful things we just talked about, because, well, if you run gradient descent, the thing is not just going to come out orthogonal, perfectly ordered, and all those things, right? It's just going to minimize the loss and find you a solution. So we lose more here by shifting away from our nice linear algebra thing, but we may still want to do it for roughly the same reasons. And on your assignment, you'll do robust PCA with the L1 loss, and then you'll do something like this. Okay, now there's actually a third approach. So not just SVD or some optimization thing, but there's kind of a middle ground, I suppose, called alternating minimization. And we actually did alternating minimization when we were doing k-means. We just never said those words. But here's what we did. We fixed Z and said, I'm fixing the cluster assignments. I just want to find the best W. And when we set the means to be the average of all those points in a cluster in k-means, that is the optimal thing to do if you're minimizing the L2 loss. That is minimizing the loss when you're fixing Z and only changing W, although we never said it in those words. And then we said, let's fix W and play around with Z. And that was going to assign each point to the closest cluster. And again, without saying it, we were actually picking the Z that minimized the loss. So we can do the same thing with PCA. We can fix Z and get the best W, and then fix W and get the best Z. And you could also think of this as a form of coordinate descent, if that means anything to you. Maybe those taking computer science 406, that was mentioned, I don't know. If not, that's fine. But basically alternate back and forth between these two. And there's a lot of nice properties about doing PCA this way. And basically, while the whole thing is a bit of a mess, jointly finding W and Z, fixing one and only finding the other is kind of like a least squares problem. It's actually like a bunch of least squares problem at the same time. But it's basically our good old ordinary least squares loss. Like if you consider X to be like the outputs and Z to be like the features and W to be like W. It's kind of a matrix-sized version of that. But it turns out we can do that with the normal equations if we wanted to. So we can do those inner loops either with gradient descent or whatever, or with the kind of normal equations-esque type thing. And if you want, you could call that alternating least squares or something like that. Okay. So alternating steps. Take the gradient only with respect to W. Right. So that's essentially what I said. We have something that looks very much like the normal equations, but one more higher dimensionality, right? With finding a matrix instead of a vector. But it has the same property, which is that the gradient is a linear function of the thing we're looking for, and so we can solve it by doing some linear operations. And then the same thing happens with Z. So I'm not really digging into these things because I don't have time, and I'm not really expecting you to be able to derive them, but to be aware that they exist and the fact that you can play these kinds of games. I also kind of think of it as alternating minimization when trying to improve the course in a kind of funny way. Mark teaches the course, gives me his slides and assignments, then I give it my best shot, give him those, update everything, give them back to him. He takes my thing, updates the course, and kind of back and forth. And I'll leave it to you to decide if it converges to any sort of reasonable optimum. Okay, so when W and Z are considered all the variables that we're optimizing with respect to, then, well, we shouldn't be surprised the thing is not convex. I mean, we just talked about how there's like a bajillion forms of non-uniqueness. It's true that non-unique doesn't imply non-convex, but it shouldn't come as a shocker that this thing is non-convex. But things aren't so bad. So there are some results, which again, I'm not going to go into, that say, well, there's two things. First, the fixed Z, optimized W, fixed W, optimized Z, those things are convex. But also, even the whole thing, even though it's not officially convex, it's kind of okay. In the sense that if you initialize randomly, you should expect to get to a point that is a global minimum. And you know it's not going to be the global minimum because we just talked about non-uniqueness. But long story short, if you just run gradient descent on this thing, either alternating or not, it should be okay. And we can also do stochastic gradient when we have, again, the benefits of doing this. We expect them to be larger when we have large data sets. And the way we can think of it is that our inner loss, well, we just have the sum over I and j, right? We have this Frobenius norm summing over all the, we're trying to reconstruct this matrix X, so we have the sum over both dimensions of the matrix X and our loss. So we can think of picking a random point as picking a random ij. And we can sample those and do stochastic gradient. And now if I pick a particular ij, then the vectors affecting that value will be zi and wj. So those will be the two things we're updating. So it's a little different than what we saw before with stochastic gradient in the sense that what we saw before, I picked a training example and then I updated all my parameters. But now things are a little bit different that I pick a, can't really call it a training example anymore, but I pick one of the things that I'm summing over to get my loss, which is an ij pair. And now not all my parameters actually influence that value. So the gradient with respect to all the other z's, all the other rows of z, for example, those gradients are just 0 because those z's have nothing to do with this point. So another way of saying it is that I only need to update the particular row of z and the particular column of w. Okay, so that's pretty much what I wanted to say about optimization for PCA, which was quite a lot. It was you can do SVD and get all these nice properties. They're in order. It's great. They're orthogonal. You can abandon that and then go a whole bunch of routes, straight up optimization problem in terms of W and Z, either stochastic or not, or play this alternating trick, which, I mean, you're not going to always want to do that. Like if you're just doing a regular least squares problem, you're not going to say, okay, I'm going to do the first half of my W vector and then the second half of my W vector. That's just weird. There's no reason to do that. But there is a reason to do that here in that when I freeze part of my parameters and only optimize with respect to the other parts, that optimization problem has a special structure that we can take advantage of and is nice. And so it makes sense to divide our parameters into those two groups and just alternate them back and forth. And again, you can think about that as what we are already doing with k-means. Okay, so I want to talk a little bit about choosing k. I'm just going to, well, okay. Just don't mind the red thing for the moment. You may hear this thing, variance explained. It's this very common thing people say when they talk about PCA. It's really just the loss we've been talking about, but written in a certain way. So the variance of these xij values, by definition, it's the expected value of the values minus the means squared. We've already centered the thing. We don't care about the means. So it's really just the sum of squares of these things. So a score we can use to say how well we're doing is this variance explained thing. It's like you have this much variance in the data set. How much of it did you explain in your reconstruction? And there's this whole maximizing variance way of teaching PCA, which I completely bypassed. I think I already showed you 5, 6 different ways of thinking about PCA. But there's yet another one, which is this thing of maximizing variance, which was I pick my first principal components along the direction where the points varied the most, the direction of maximum variance. Because if I had points all the way over here, this is a good line, because there's a lot of change along that direction, and I want to capture that change when I project down to it. Whereas if I pick the other direction, I'm kind of throwing away all those changes. So it's, again, mathematically equivalent, just yet another way of thinking about it. And it's essentially saying how much of that variation did I lose when I ran this PCA. So this thing is actually just our loss, but normalized by something having to do with the data set. And 1 minus that is the variance explained. So this is like the variance unexplained, I guess. And this is a score between 0 and 1. If I have a perfect reconstruction, then I have 0 in the numerator. And if I have ZW just giving me nothing, then I have like x over itself. So, well, maybe it could be more than 1, but probably not. Okay. So just be aware if you see someone saying variance explained or maximizing variance or whatever, it's just the same loss, but normalized. And if I normalize, that doesn't change the loss, right? We said we can multiply a loss by a constant. So if I minimize that or minimize that divided by some constant or maximize 1 minus that, they're all the same thing. But you're likely to encounter those words. So we did a lot of things today. We talked about the loss that we use for PCA, which is the squared reconstruction error, the reconstruction being Z times W, the projection onto the subspace. We talked about all the ways in which different W's imply the same hyperplane or subspace. We talked about ways to get rid of that redundancy, and SVD, which is for the moment just this black box, but does all of that for us. And then we talked about some other ways of computing the thing, this alternating minimization being a more general concept, but then we're applying it here. We're alternating between ZW, ZW, and that's the one that you'll do on your assignment 5. And then it's a bit of a stretch to say I talked about choosing K. I did talk about the variance explained thing, and you can choose K by the same kind of ways as with K-means. by, for example, looking at how the loss, or likewise this variance explained thing, changes as you change k. And it's again pretty iffy, but you try to pick a point where it looks like you have diminishing returns, basically. So that is it for today. We'll see you on Friday.